There it is. And just a word on the lab for this week. First, I just want to show you where it is in case you haven't gotten that pattern down yet. And so I'm going to share Google Chrome with you if that's all right. This is the modules page. You can see this is all the chapter 13 material that we're doing right now on fluids. And then right below it is the blood pressure lab for today and tomorrow, for those of you doing it tomorrow. It's our last lab. It's fairly short. This one's only worth 25 points. I have nothing more to tell you tomorrow. So I will be on Zoom answering questions at 9:30 for the morning session, and I guess it's 1 o'clock for the afternoon session. Dr. Kem, I assume, will see all his people this afternoon. In years past, we actually have a series of blood pressure cuffs. I guess we have about 8 or 10 of them that you would put on your arm, and you would make measurements of your blood pressure in a normal position by your heart, where the cuff is by your heart. You'd lift your arm over your head, put it off to the side. You'd put the blood pressure cuff on your ankle. And what we talked about last class, the difference in the pressure at all those points ought to be equal to that thing I called the gauge pressure difference between those points. So it'd be rho, the density of your blood, times g, the acceleration due to gravity, times the difference in height between those points. And so you can see my arm being right here has a different height on the blood pressure as I move it up. It may 10, 15 centimeters maybe is the difference, but that does register a difference in blood pressure that is measurable. You can see it on a blood pressure cuff. Unfortunately, of course, we're not in Dunning Hall. But I have a blood pressure cuff at home because I'm old, and old people watch our blood pressure all the time. So I did all the measurements on me that we would normally have done in Dunning Hall. I gave you little pictures of my blood pressure readout. You could just use those numbers and do the calculations with those numbers. Lab's worth 25 points. If you happen to have a blood pressure cuff of your own and you don't want to use the readings on me, you want to use the readings on yourself, well, that's going to be extra work for you, obviously, and I'll give you 5 extra points. So you could potentially earn 30 points out of 25 if you have a blood pressure cuff available and you want the extra credit. Even if you have a blood pressure cuff available and you just want to use my numbers, that's fine. I can tell you I've done the calculations. My numbers work. You'll get reasonable results. But if you want to just do the experiment like we normally would have done in Dunning Hall, 5 extra credit points. If you're at a marginal grade, you want that, you're at a B+ and you want the A-, maybe that's the difference. You can do the math and figure that out. Feel free to do it if you can get a hold of a blood pressure cuff. I recognize that a lot of people can't, and that's why I just did it on myself. Okay, so that's the lab this week. I have nothing more to say to it other than that. The only thing Dr. Kem may want to talk about is just to tell you about what density to use maybe for blood. It's near to water. So if you use 1,000 kilogram per meter cubed, which is the density of water, you'll probably be okay. I think because of the solids that are in your blood, the density goes up just a little bit. Our book value, there's a chart in the textbook. It says 1,060 kilogram per meter cubed is the density of blood. Neither the difference in those two numbers is inconsequential for this lab. So use whichever number you want. If you make measurements on your own arm and your own ankle height to arm, obviously you need a meter stick or some kind of tape measure to figure out those dimensions. The ones for me are obviously different. I'm kind of tall. All right. Any questions on the lab this week? As I said, I'll be around. My one warning, if you're in one of my sections, Zoom turns me off. It cuts me out if I'm inactive for 40 minutes, and I might be working on some other thing and have multiple windows on my computer on top of Zoom and may not see that it logged me off. If you need help and I'm not there when you come back into the Zoom meeting, just send me an email and that'll make a little ding, and then I'll see it and I'll see that you need help and I'll log back into Zoom. 40 minutes of inactivity, it logs me off. It just bounces me out of the system. Okay, so that's tomorrow. I will be around all day, both in the morning and in the afternoon session to help. All right, any questions on the lab? All right, then I'm going to move on to the topic of today. And you can almost see fluids in two ways. Monday, we talked about a static effect, right? You've got a column of water whose weight is acting on either the vessel that it's in or maybe the bottom of a pool or something like that. Everything's nicely at rest. And, you know, it's kind of the Newton's first law of fluids. Things are just hanging around at rest. We're going to talk about another effect today where it's just a static effect. It's a Newton's first law kind of problem. And then we're going to move into where fluids start moving, more of a Newton's second law or an energy conservation sort of problem where things are having a velocity. And so that's the transition today. We'll pick up more of the rules for moving fluids on Friday, because we'll be talking about something called Bernoulli's principle, Bernoulli's equation on Friday. So we're going to talk about two things today. The worksheet is sort of a mixed bag of things that are at rest and things that are moving, and hopefully the problems make sense, particularly if you watch my video. I did two these Archimedes principle, these buoyancy problems last night. If you have any trouble with the worksheet today, I'd refer you right back to that and just do it the same way. You have to think about these problems, though. They're not difficult, but if you just start grabbing densities and you're not thinking about what actually is going on, if you're not drawing a picture, intellectualizing and thinking through the problem, you'll just put the wrong number in the wrong spot and get the problem wrong. And that's a significant issue. And hopefully that'll make sense to you. Okay, so let's run on over to my PowerPoint. And okay. That's bizarre. I would move that a little bit. I'm not sure you're seeing that, so I'm going to stop sharing it, move it over to the screen where I have two monitors going, obviously, and that sometimes confuses Zoom. So let's put it over here so I can make sure that when I share it with you, you actually are seeing it. All right, definitely seeing it there. I see the green border around it, which tells me you are. And here's the first kind of statics law. And that's an object at rest here, but it has a new force that we add to our catalog of forces with weights and normal forces and tensions and forces from springs, the force of buoyancy, the force that a fluid exerts on an object which is submerged in it. I mean, and submerged, it isn't only with respect to water. You could be submerged in a gas too, but a buoyant force is always put on an object that is in a fluid. And how big is that buoyant force? Well, Archimedes is the guy who gets credit for having put a rule, a law into effect, which has been verified by experiments over and over again. He said that the buoyant force, we'll just call it an F with a subscript B. Sometimes I'll get a little sloppy and I'll write just a capital B, just like we write capital T for tension sometimes. Okay, the good news is in this semester, there is no other force that begins with B. So F sub B or B works just fine. That force in magnitude is equal to the weight. So it's just a weight, it's an M times a G, but it's the weight of the fluid which is being displaced by the object. And then that force just acts as another force in your free body diagram on that object. And so that's the equation right here that's in the Washington College, I guess, maroon box. The buoyant force is equal to the mass of the fluid, could be water, okay, times the acceleration due to gravity. Now there's a kind of another equation buried in here, right? And that's, okay, how do you get the mass of the fluid which is being displaced? Generally, what you can measure is the volume of the fluid which is being displaced, right? And so let's pick a nice color pen here, just that obnoxious red. And so I might know that thing's a cylinder right there. Hopefully you know that the volume of a cylinder is like what, pi times its radius squared times whatever the height of the cylinder is. That's the volume of the thing. How do I get the mass of the thing? Well, you take a volume and you multiply it by a density, and that gives you a mass. And so that's this part right here. And now the important thing is you might be given multiple densities in a problem. It's the density of the fluid is the one that you pick. Okay. And by the way, that is the volume of a cylinder. I put that out because over the years I found that's an equation right there up to density. That's an equation people don't know. Here's another one that you might need. What if the object is a ball, some kind of sphere, or maybe it's a balloon, and the best approximation you can give it is a sphere. The volume of a sphere, SPH, how's that? SPH sphere is equal to 4/3 pi, that's a 3, 4/3 pi times the radius of the sphere cubed. Now, it's a volume, has to have density, has to have units of volume, so that in density, which is mass per volume, you cancel the volume. It has to have meters cubed. See right here? Radius would be in meters. You square it, that's meters squared. You multiply by the height of the cylinder, you got meters cubed right there. For the volume of a sphere, you can see it's already cubed. So if you have radius in meters, you're going to get meters cubed right there. I see people using area equations, like when they want a volume, they'll write something like pi r squared for the volume of a sphere. Well, no, that's the area of a circle. You can see right away it has units of meters squared. So that's an area. Don't use that in this case right here. Hopefully you realize that if it's a kind of a rectangular box being submerged, its volume is its length times its width times its height. Okay, just multiply those things out. And so that's how you figure out the buoyant force. And generally, you'll be given enough information in a problem to figure out what the size of the thing is, what its volume is. You'll be given the density, or you'll be able to look it up on a table, and you'll be able to figure out what the buoyant force is, because of course you know the acceleration due to gravity. It just becomes a force you add to a free body diagram. All right, any questions on that? That's Archimedes' principle. Don't confuse the densities. Make sure it's the density of the fluid that you're using, whether it's air because it's a hot air balloon floating around in air, or it's the density of water because it's an object like this submerged in water. That's the density you use right here in Archimedes' principal equation. But at the end of the day, it's as easy to remember as weight, mass times an acceleration due to gravity. But what mass? The mass of the fluid, which is displaced by the object, which the buoyant force will act on. And it just becomes another force in your free body diagram. I'll have some questions on that in a second, just to hopefully solidify that. All right, then the next thing we went on to is a fluid moving in a container, some kind of pipe system maybe. Okay, going, it could be I heard the vaccine is working real well here, that Pfizer is going to have a vaccine out. This could be a little shot plunger right here, forcing fluid through some narrower channel like the needle into your arm. And if there is laminar flow as the material, as the fluid goes through this container, well, there has to be continuity of volume flow of the fluid per time. And as long as the flow is smooth, that's guaranteed. If you think about it, it has to be. When we say continuity of flow, we're saying, hey, there's no leaks in this tube where, water or fluid or whatever it is leaking out. There's no inlet pipe where we're adding more fluid. All the fluid that's there over on the left side has to come out the right side. So the number of both kilograms per meter or per second per time, and then the volume, assuming it's incompressible, also has to be the same, going in on the left and coming out on the right. We call that a continuity equation. We showed last night in the video that it is then the cross-sectional area over on the left times the velocity on the left. That will give you units of cubic meters per time. Look at the units, area, meter squared, velocity, meter per second. So that's the volume per time over on the left side, has to be equal to the area times the velocity on the right side, the volume meter cubed per second on the right. Assuming we don't lose any because we got no leaks, nobody's throwing any more liquid in, any more fluid in, that has to be true every time. Now, there's some other things we'll talk about on Friday, like what's the pressure at various points? And what if this little pipe is going upwards, uphill, and you have some more potential energy that you got to give to the fluid? Those are things we'll address on Friday. But for now, assuming things go horizontal, that's our rule and that's our law. Assuming we have laminar flow, We don't lose any mass. We don't lose any of the fluid. We don't gain any mass. We don't gain any of the fluid. Got to be continuous. What comes in has to go out. And that's fairly sensible law, hopefully. All right, last chance for questions, and I'm going to ask you some. All right, let's move on then. This is, to me, a little bit like War of 1812. When was it fought? I don't know. Let's think about it. So hopefully this one's easy. There are some that are a little more subtle, but let me find the poll now. There it is. Zoom always puts these things in different places just to make my life interesting. There it is. Launch the poll. And it's also related to which weighs more, a ton of feathers or a ton of bricks. Heavy lead block, light aluminum block of equal size are both submerged in water, upon which is the buoyant force greater? This is the easy one, by the way. Hopefully everybody's doing well, so that's good. They'll get a little more subtle here in a second if you say, is this all he's got? We'll get a little more here in a second. All right, looks like 21 and 25, 22 and 25, coming up on a minute, but it's the easy question just to get you warmed up. All right, I'm going to cut it off right here because most people got it. Share the results. Absolutely. If they are the same size, okay, equal size, that means they have the same volume. They're both in water, the same fluid, so the density is the same, and the acceleration due to gravity is the same. The buoyant force will be the same. Now, if you're drawing a free body diagram, of course, the lead has a big weight. That's the lead. The aluminum has a little weight, right? There's the aluminum. And if the buoyant force is the same for the two because they're the same size, well, the effect on the aluminum might be an upward force. The effect on the lead might be a downward force based on those relative sizes. But the fact is the buoyant force here, which is upward, always upward in a fluid, is the same, okay? So that's good. And this construct of drawing a free body diagram is going to be important for the harder questions which are coming. All right, so good job on that one. Yeah, that's the experience the same buoyant force, and I explain why that's the case, because they have the same size. And so let's move on to the next one. This one's a little more subtle, and hopefully you can picture it in your mind's eye what I'm talking about here. So I've got a big pool, and let's see, the lead, I guess, sinks to the bottom, like those rhinos in the pre-lecture video where I talked about them walking along the bottom of a river or a lake. So there's the lead. And the other is wood, and it floats. So I'm thinking there's the wood, okay? I don't know what, there's no chemical symbol for wood, so we'll just write wood right there. And that's the question, which one has the higher buoyant force? Same size, again, just like the aluminum and the lead in the previous problem. Identical size, but the wood is floating like I've drawn right there. The lead's at the bottom. That's a B. Yeah, this is a little more subtle. All right, I got 26 people now. I think 22 people played last time. We'll give whoever that last person is, maybe they're having internet issues, give them a second. All right, about a minute 15. I guess we're done. So let me share the results. And I can almost live with C. In fact, when I first thought about this, I was having trouble picturing what the wood looks like, because sometimes wood floats in water just like that. Okay. In which case, since they're the same size, the volume of the wood that's submerged and the volume of the lead which are submerged are exactly the same, in which case I would say they both would experience the same force. So I'd agree with people who pick C. Then I thought about it. Most times when wood floats, some of the wood is out of the water. It's propping up through the water just a little bit. Kind of like if you think about an ice cube near the top, there's a little bit of the ice cube that's sticking out over the top of the fluid. And so the result is there's less volume of wood that's displacing fluid, that's inside the fluid, as compared to the lead, where all of the volume of the lead is displacing the fluid. In that case, this thing right here is less for the wood, greater for the lead. And so even though the lead block is sitting on the bottom, more of its volume is displacing volume of water. More of it, it's completely submerged as compared to the wood, which might be partially submerged. Greater buoyant force then, because greater amount of water is being displaced. Okay, a little bit counterintuitive. I can live with C if the way you pictured it was, although the wood is floating, it is still completely submerged so that the same volume of water is displaced in both cases. I could live with C in that case. But if it's truly floating and it's popping up out of the top of the liquid, less of the volume is displacing water, less buoyant force. Okay. The only reason it's floating is because of the difference in densities. The lead is significantly more dense than the water, and that's why it sinks. Whereas the wood may be not as dense as the water, so it floats. Okay, which I think proves a point to you, which is more dense, ice or water. And since most people experience ice as floating, it must have a density less than that of water, and it does. Ask a chemist. All right, any questions on that? All right, because that's going to lead into the next question, I guess. Let's see, anything else I want to say on here? Yeah, this fully submerged lead block displaces more water. So that's why the lead block is having a greater buoyant force. This one's, I stared at this one for a long time, I'll be honest with you. I eventually saw the pattern. I'll show it to you, but I won't be surprised if many people get this one wrong, because now we're asking about that density between the lead, density between the wood. So I have 3 different blocks of 3 different sizes, made of 3 different materials. And the question is, which one's the most dense, based on your observation of how they float in this container here. That's good. Most people, I didn't leave the answer here, did you? You guys are doing better than me, because most people are getting it right, which is reassuring, because I had to stare at this for a long time. Of course, I had to figure out how I was going to explain it to everybody. Okay, but eventually I figured it out, and most of you are getting the right answer here. And a free body diagram helped me a lot. I'll end the poll here. Are you able to see this? Oh, are you cheating? I'm going to make these smaller so you can't see the answer on the next slide. All right, here's the reason, though, regardless of how you got it right. I'm going to share the results with you, and I'm happy that everybody saw the right answer. Maybe better if you can see it. I looked at the free body diagram and I said, okay, compare this volume right here, which is what we just talked about when we talked about the wood, right? Compared to this volume right here, submerged, which is the thing that gives us the buoyant force, right? And then compare it to this thing right here. Well, to me, the buoyant force from B and C looks to be about twice the volume submerged as compared to A. So these 2 buoyant forces look about the same to me, roughly, maybe not exactly, but both pretty big. The buoyant force on A seems to be less, doesn't it? Okay, about half is less. It's about half the area maybe submerged compared to B and C. But, and here's the but, what about the relative size? It looks to me like, oh, I don't know, compared to A, if I tried to put A here, there's at least 4 times the volume, 4 times the size of block B here compared to A. And half the or twice the buoyant force. And so if it's got 4 times the size, but it only takes half the buoyant force to keep it up, I think this has to be less dense. Okay, this must be a pretty dense thing if 1/4 of B is being floated with a buoyant force that's half as big, the difference between the 1/4 and the half. I looked at C and it kind of looked like thirds for size, 3 times A. And again, bigger buoyant force also would be less dense. And so block A, I think, is the right answer. It's the most dense. For the size, it has the least buoyant force, but it's half the buoyant force, but its size is significantly less. So it has significantly less mass for the same required buoyant force. Okay. I'm sorry, I said that wrong. Significantly less size for the same buoyant force, which means it has a greater density. And so A is absolutely the right answer. Maybe a little bit better picture of that right there. There's A, and there's like 4 A's right there. Only twice the buoyant force, not 4 times the buoyant force, which you might expect from sinking 4 times as deep. Maybe 3 times right here for this one that's kind of vertical. And so I think A has to be the most dense because it's the smallest thing with a pretty big buoyant force anyway. All right, stop sharing that. Move on to the next one. That's the most subtle one. This one, same thing, free body diagrams. And let me get to the bottom here where it puts my question. So you got 3 blocks. Notice they're all the same size. 2 of them have the same mass. And then the question is, what's the order of the scale readings? Which one has the biggest reading on the scale? And really is saying which one is supplying the biggest tension, perhaps, to cause the thing to float. So think about free body diagrams. Yeah, all over the map on this one. All right, I'm going to end it right here and share the results with you. You can see all over the place, pretty much evenly split. E, unfortunately, is, although the majority view, not the correct answer. And here's what I think. So let's look at all the blocks, which are the same size. So that means each block, because it has the same volume, has the same buoyant force. Identical length vectors right there because they are all the same size, have the same volume, same buoyant force. Now, let's see. These 2 are the same mass. So they have the same weight, don't they? This one right here has a bigger mass, so it has a bigger weight. And if I probably should be labeling these weight C, weight B, and weight A, which are the same. Okay, well, they're at rest. They're not moving up and down. That's how scales work. The thing comes to equilibrium. So I guess the tension here and the tension here, which is being displayed on the scale, because they're the same weight and the same buoyant force, presuming that the weight is bigger than the buoyant force because they're not floating to the surface, the scale would have to supply the same amount of tension in case A and B, because the buoyant force and the weight are the same. And so all of a sudden, I've got two possibilities now, because I think the scale reading for A and B are the same. So the rest are eliminated as choices. It's either A or B. And now you got to look at the free body diagram for C, and you go, well, the weight of C is bigger. So that must mean in order to be at equilibrium, the tension supplied by the scale is bigger. And so I think C is the greatest reading on the scale because it has the greatest tension. That's what the scale is displaying. And A and B are the same. And that was the thing that delineated the answer. Okay. And so there's my choice. Now, some of you probably were concerned about the height of these things, the fact that B here was at a lower height. And you might say, well, doesn't that mean it's got a greater pressure because it's deeper in? And that's what we studied on Monday. The answer is yes, it does. But that, in the case of an incompressible fluid, doesn't affect the density. And if you're really concerned about a derivation of this, while the pressure is greater at the bottom here than it would be at the bottom of A and C, it's also greater at the top as compared to A and C. And since they're all the same size, the difference in the pressure between the top and the bottom of the block is the same. And that's what gives rise to the buoyant force. Okay, it's that difference in pressure between the top and the bottom. We didn't do a formal derivation of that. If anybody wants to see it, stop by at office hours. I'll be happy to show you how that is derived. But it is that pressure difference. The only time the deeper one might experience a greater buoyant force is like in a very deep ocean area, where as you go deeper into the ocean, the density actually gets bigger because of the compressing from the weight of the water above it. In our class, we're assuming that the fluid is incompressible, and so we don't have to worry about that effect. Okay, so in a fairly small thing like this, where the difference in height is small, we don't have to worry about the fact that it absolutely has a higher pressure in the deeper one, but A and B are really the same thing. They're both in a static equilibrium state, and so just work it out using a free body diagram. All right, questions on that? Last one then. And then I've got a couple problems to do. And this has to do with that continuity equation here that we were talking about. And so I guess I've got a 2 centimeter diameter hose and a 3 centimeter diameter hose. And the question is, where is the velocity greater? V1 or V2, or maybe V in the 2 centimeter hose as opposed to V in the 3 centimeter hose. And remember, we said, I'll go left and right here. All right, looks like most people have it and have the right answer, so I'll end it and share the results. This time the majority does indeed win. The 2 centimeter hose has the smaller area, right? Pi r squared, so it must have the bigger velocity compared to the 3 centimeter hose, which has the higher velocity and therefore has the smaller velocity. So absolutely, the 2 centimeter hose is the winner. All right, stop sharing that. Any questions on anything we did right there? The subtle one, I think, was the 3 different shaped blocks that are submerged differently, and you had to get density out of that. but it's doable. I'm going to stop sharing this. I'm going to now do a problem on what we just talked about right there. If I can get screen mirroring to work here and max airplay. Come on. Look at that. Come on. Don't have to load the utility. That's good. And so here's our firefighter. And a couple rules up at the top we'll talk about if you need them. There's our firefighter, exactly the problem we were talking about. He has a fire hose with an inner diameter of 10 centimeters. Okay, so let's kind of draw that. This diameter, and be careful here, D is equal to 10 centimeters. What's that mean the radius is? Think about that. Okay, then he has a nozzle. Let's draw the kind of simplest kind of nozzle you can have, just a cone. And the diameter right here, of course, that's connected, right? Some kind of, so you screw it on the end. And this distance right, well, that's terrible looking picture. Let me try again. Come on. Try again right here. There's my nozzle. And right here, that diameter is 3 centimeters. Okay, so you can see this thing changes. And I know that the water leaves the nozzle right here, moving at 50 meter per second. Okay, and so that's kind of the given information hung on a reasonable diagram. That's all you need, just a hose with a funnel at the end, a cone that has an opening. And the question we're being asked is, okay, what's the speed back here? And I've gone with the 1, 2, left, right construct, whatever you want. I'll call this 1 and this 2. And we said the simple equation, hopefully, is A1 times V1 is equal to A2 times V2. Now, the last polling question that most of you got right would tell you that I would expect for the bigger cross-sectional area, I would expect a smaller velocity here for 1. And so when we're done with our math, that better be what happens, okay? And so what do? Well, I guess I go pi times radius 1 squared. Radius 1 would be 5 centimeters times velocity 1 is equal to pi times radius 2 squared. Radius 2 would be half of 3 centimeters, 1.5 centimeters times velocity 2. I don't have to put pi into my calculator if I don't want to. It's on both sides of the equation. Let's just eliminate it. And so it looks to me like velocity 1 is equal to the radius 2 at the nozzle squared times velocity 2 at the nozzle divided by radius 1 squared. And so now it's time to put numbers in, right? We said 2 would be 1.5 centimeters squared times 50 meters per second. And then I divide that by, let's see, radius 1 is 5 centimeters squared. And I did that in my head. You could just divide by 2 and put the 3 and the 10 if you want, but make sure it's inside the squared parentheses, okay? Make sure you don't forget to do that. You could spend time converting units here into meters. You could. I don't see a reason though, because centimeters squared cancels in both, and I'm left with meters per second. And when I put this into my calculator, I got 4.5 for the number, 50 times 1.5 squared over 5 squared. And then the only units I have left are meters per second. And so that's how the continuity equation works. Pretty straightforward, I hope. All right, any questions on that one? All right, one more, and then I'll give you time to do a problem. And so let's slide, and I'm going to do this one. I have to be honest with you. This is Pascal's law. We didn't have it on the worksheet for Monday. And if you're ever tested on, say, the final exam on Pascal's principle, I really don't know any other problem to give you other than this one. We actually did one of these in the pre-lecture video for Monday. We talked about this in polling on Monday. We had some, and it always looks like this. This is how we test Pascal's principle. I have no other question I can, in my most creative day, come up with besides this one. In any event, what we said is, if on the left side here, I apply a force over the area, and you're seeing a cross section. If you looked at it from the top, it would be a circle, okay? And if you looked at this one from the top, it would be a bigger circle. So I guess we said Pascal's principle is the pressure on the left will be equal to the pressure on the right. So if I push over here with some force, the question is on the right, how big a force do I have to push on to give the same amount of pressure on the right and left? Because that's it. And you know, if you didn't put this amount of force on, what would happen is the thing would rise up. And often that's what we want. Like we want a car to raise up, or we want to lift a boat or something like that out of the water. And this is how hydraulics works. Okay, so let's see. On the left side, the force was given as a little f divided by a little area. On the left side, it's a big force, capital F, that's big, divided by a big area, right? And we're asked from these numbers, the radius of the piston on the left is 0.12 meters, on the right, bigger, 0.65 meters. And if F was 14 newtons, higher than what it used to be, which maybe at 0 was what it used to be, what would be the force on the right side that would be necessary to keep the thing from moving? If you didn't put that force on it, it would move up. All right, so we're solving for F here. F is equal to, just bring the area to the other side of the equation, which, put the numbers in now, is 14 newtons times, let's see, pi times, are we given radius or are we given diameter? Always check for that. In this case, we're given radius, so I don't have to divide by 2, 0.65 meters squared, okay, divided by pi times the other radius on the left side, 0.12 meters squared. You know, I'm not putting pi into my calculator. That's a waste of work. It cancels. The meters squared and the meters squared cancel. And all I have to do is put those numbers into my calculator and I'm good to go. 411 newtons. So what does that mean? 14 newtons over here. The mechanical advantage gained is I can put a force up to 411 newtons on the other side and everything will stay at rest. If I put something with less than 411 newtons of force, maybe it only has a weight of 300 newtons, well, that thing's going to get lifted up, isn't it? And that's how hydraulics causes motion. Okay, often done in a controlled manner. You don't put the 14 newtons on all at once, but you put a small force here. The result is you get an amplified, a big force right there, just like a lever would give you, okay, if you made the lengths appropriate to a lever. Questions on that? All right, here's the problem you get to do. And I'll draw the picture for you. And I guess now you got about 6 minutes. You can run the calculation real quick. We got a boat. That's how we draw boats. You can see the pointy end. And it says that there's a solid titanium sphere hanging from the boat. Okay, completely under the surface of the water. Yeah, okay, great. We know what the density of seawater is. Fresh water is about 1,000. Seawater has that salt in it. It's a slightly denser fluid. 1025, I've seen 1030 kilogram per meter cubed used. Okay, the density of the titanium here is also given to you because all you know about the titanium sphere is its radius. Okay, that's the given information. So it seems to me, and this is the last thing I'll help you, well, next to the last thing I'll help you with, I guess, your free body diagram here, weight, that's the weight of the titanium, the tension in the cable, and of course the new force for today, the buoyant force, F sub B or just B. And how do you get it? Well, weight, just like you've always gotten it, it's M times G, but you're not given the mass. You have to take that density and you have to multiply by the volume, and that's the density of the titanium. I think titanium is Ti, is its chemical symbol, times G. The buoyant force, on the other hand, is the weight of the fluid which is being displaced by that thing. So that's a density times a volume times G as well, but now that's the density of the fluid, right? And of course, the difference, the free body diagram will tell you that the sum of those three forces has to be equal to 0, and that should allow you to solve for the tension that's holding the titanium ball up. Any questions on that? All right, you got about 5 minutes, work the numbers, 4 minutes now, work the numbers in your calculator real quick, upload that one into Canvas by, I guess by Friday, today's Wednesday, and we'll be good to go. I'm not gonna break you up into groups. It'll take a minute to do on either end, but if you got any questions, feel free to pipe up and ask them. If you've already got the answer and you're ready to upload it, give me a second to create the assignment, and we'll see you on either lab tomorrow if you're in one of my sections, or we'll see you on Friday. And I will be back at 10:30 for office hours today, for those of you that have to leave.
Thank you.
You bet. Anybody got a number they want to see if it's correct?
I have a quick question.
Yeah, go ahead, Jackie.
So for the weight, it would be the density of the actual ball, right? Not the water?
Yeah, it would be the 4,500 right there for the weight. Whereas this one, the buoyant force would be the density of the water times the volume times G, right?
Yeah, okay.
Okay, and then the difference between those two, that must be the tension in the cable. Yeah, that's how this problem works. But was it you who asked, is the final exam review? Is it, and I'm not going to go back and ask a Newton's first law problem, but in order to do this one, you kind of have to know Newton's first law, that the sum of the forces are equal to zero, don't you? Physics sort of naturally uses stuff from earlier in the semester to answer current problems. And it's just the nature of the physics. A lot of sciences are like that, though.
Dr. Sokolsky?
Yeah.
How do we know that the weight is the density times volume times G?
Well, let's see. Let me share my iPad with you here so I can draw. Look at that. All right. Now, what does density mean, I guess, okay, but don't go away. All right. Hopefully you're still seeing it. Yep, looks like you are. The definition of density is how much mass you have divided by the volume, right? Kilogram per meter cubed. And so what I'm saying is, well, to get the mass of the titanium ball, you take its density and you multiply by the volume. In this case, the volume of a sphere, which is 4/3 pi times its radius cubed. So that gets you mass. And then in order to get weight, well, it's just mass times G. And so I've substituted in for mass the density of the titanium times the volume. Does that answer your question?
Yeah, that makes sense. And then for the buoyant force,
right?
I'm just having trouble like how to get that.
Okay, same volume, right, that you used here, still the volume of a sphere, 4/3 pi times the radius cubed. Only now the buoyant force, according to Archimedes, is not the actual density of the titanium sphere, but I'm sorry, not the weight of the titanium sphere. According to Archimedes, the buoyant force is the weight of the water, which isn't there because the titanium sphere is in its place. So that we say it's displacing the water. Okay, so exactly the same equation. It's mass times acceleration due to gravity, but this time the mass, still density times volume, but now the mass is the density of the water times the volume. And of course, in order to get the weight of the displaced fluid, I multiply by G. And so I think the two equations, oddly, are exactly the same, right? Density times volume times acceleration due to gravity. But for the weight, you're actually using the density of the thing whose weight you're trying to calculate. For the buoyant force, you're using the density of the water, the fluid which is being displaced here.
Okay, that makes sense.
Yeah. And you know, that's why we say the reason that the titanium, if it wasn't for that cable, would sink is it has a greater density, right? Something with less density than water would actually float up to the surface, perhaps, or at least be neutrally buoyant if it was exactly the same as the water. Oil, for example, is less dense than water, and that's why it actually floats on the surface of water, because of the comparison between these two numbers for oil and water.
Okay.
Right?
Yeah.
Can I check an answer?
Sure, go ahead.
For the tension, I got 6,100.
Yep, that's what I got.
Okay.
Yeah.
Thank you.
You bet. Not bad, was it? Not too bad.
Okay, so Dr. Tahosky, I also got 6,100, but I still don't think I really understand the concept of buoyancy like at all.
It's now the only real answer I have on buoyancy. Let me scroll down here. I can draw another picture, maybe a little bit neater for you here. All right. So here's kind of how it works.
Mm-hmm.
Bye.
Take care now. So let's put an object right here. Okay. And fluid. And I made it a square, a rectangular kind of cube instead. And what we learned on Monday is there is a pressure at the top and there's a pressure at the bottom, right?
Yes.
Which one's greater?
If it's floating in the middle, isn't it the same?
Yeah, it's just kind of floating there. Just pretend it's floating for a second. I think if it's buoyant, it's going to go up, or if it's more dense than water, it's going to go down. But let's just hold it for a second there, take a picture of it, and think about what all the forces are. But the big point here is we showed on Monday that the pressure at the top is equal to the pressure. I'm going to go the other way. The pressure at the bottom is equal to atmospheric pressure plus rho times G times whatever this distance is right here, right?
Mm-hmm.
Well, that is if this is the pressure at the top. The difference in pressure is this term right here, right?
Yes.
Okay. And I suppose I could go there to there and use P0 atmospheric pressure plus rho times G times whatever those two things is. But the difference between, I don't know, call it Y1 and Y2 is going to be rho times G times that distance D. That's the pressure difference between the top and the bottom. All right, now there's an area at the top, which is exactly the same area at the bottom, right? And we've already decided this pressure at the bottom then is bigger by exactly that amount rho G times whatever the height of this thing is. Well, that must mean that if I'm looking at a free body diagram, there's a big force pressure at the bottom times the area acting on the bottom surface. There's still pressure at the top. It's just smaller. So the force there is pressure at the top times the same area. And since this force down here at the bottom is greater than this force up at the top because the pressure is greater at the bottom, the difference between those two numbers, that is the buoyant force. So the buoyant force is equal to the force at the bottom because the pressure is greater at the bottom minus the force at the top. Archimedes figures out, well, that has to be equal to rho of the water, the fluid here, times G times the volume. Put the volume right there, okay? It's the weight of the displaced fluid. And you don't have to understand how Archimedes got to that. It's actually a little bit of a calculus argument to prove it, but hopefully it makes sense that what we did on Monday, the pressure at the bottom is greater, so the force at the bottom is greater as compared to the force at the top of the object. And that's what
the difference between the forces is the buoyant force. Is the
buoyant force, exactly right. And Archimedes shows it's rho times the volume times G, where the volume, yeah, go ahead.
And the buoyant force is what makes you want to float or makes you float. Okay.
Yeah. And buoyant force is always upwards. The only question on whether it'll float or sink is how big's the weight compared to the buoyant force, right? If the weight is greater than the buoyant force, it's sinking. If the buoyant force is greater than the weight, it's rising to the surface. Now think about fish, right? Fish try to stay neutrally buoyant. And so they do things with, they have a little bladder that they have with air in their body. And so fish can either expand that bladder or shrink that bladder to change the buoyant force to be exactly equal to the weight. And then they just kind of float at a constant depth, right? And so that's another possibility. The weight's either greater than the buoyant force, it sinks. Buoyant force is greater than the weight, it rises up to the surface, or the two could be exactly equal and it just floats right in the middle. So those are your three possibilities.
Okay.
All right.
Yes. That is more clear to me. I think I might have to
now you got to work some problems, make sure you see how the units work. In this particular case, if you look, hopefully you got a buoyant force on our titanium ball of about almost 1,800 newtons. I got 1,760. And the mass I had was about 7,900 newtons, much greater. And so if it wasn't for that tension, that titanium ball would sink, right?
Okay. Yeah. So if it wasn't for the upward force helping the buoyant force, it would sink. Okay.
Yeah. Yeah, only because the weight is much bigger than the buoyant force. Hopefully that's what you calculated. And that's why there has to be a tension pulling upwards so the ball stays right where we put it. All right?
Yes. Okay. Thank you.
You bet.
Dr. Tukolsky, I have a question on lab 9.
Okay.
So this is like last week's lab.
Yeah, no, I remember. I just got to pull up. I've actually been working on this week's lab, so I have to go pull up last week's. I don't have a. Do you have a screen you can share with me with your question?
Yeah, I think I can share my
Yeah.
screen.
Yeah, if you've got it up on your computer right now, just that'll help me.
Oh, it's
Or I can pull it up. I have it on my hard drive here. I can pull up last week's lab. I don't have a paper copy right in front of me right now.
so this is like my, can you see it?
Yep, I can see it.
So this is my lab 9. So question 12 asks like, what's the physical quantity
Yeah,
that you find? Is it an acceleration?
it
Because
is an acceleration, isn't it?
okay, so
Yeah.
I got that, and I think I'm getting like the correct numbers and stuff. Like my R value was pretty good, and my
Yeah.
error
One
wasn't
thing I'm
too
going to
bad.
change on acceleration, though. It's almost
Okay.
accelerating. It has units of acceleration.
Yeah.
Remember back on chapter 3 when we talked about kinematics? If you think about what you did, you had velocity squared at the end, I guess, final, is equal to velocity squared initial. I put the subscripts in the wrong place. That's kind of silly. So when you try to talk and write at the same time. Velocity initial squared plus twice the acceleration times the displacement. And I think that's kind of what you had in this problem. Here's why. If I multiply everything by mass, and then I divide away that 2, what I'm left with is a force here times a displacement, which is the work done. And the thing that's doing the work in this problem is gravity, because that mass is falling with some weight times some displacement. So you're almost the acceleration, because you basically are looking at velocity squared versus another velocity. Well, I guess during looking at displacement, the slope isn't exactly acceleration. See, it's twice the acceleration, isn't it? Because of that too. Now, that's not the way you did the problem, but that just is illustrative of you're plotting the final velocity. You're plotting the velocity anytime, actually, versus displacement, right? That's what you're putting on your graph.
Well, the graph said to plot the final velocity squared versus
right.
The displacement. So I guess like I just didn't really understand what the point of that was.
Yeah, because well, we started the thing from an initial velocity of 0, right?
Yeah.
And if I make this plot, other than that little kind of glitch thing that happened because probably the sensor tracked off on my hand, you get a straight line, right? The equation of a straight line is that y is equal to mx plus b, right? Well, in this case, what's on the y-axis is velocity squared. What's on the x-axis is the displacement. So the slope should be the relationship between those two, which is twice the acceleration. And of course, since we started from rest, that intercept there ought to be just about equal to 0. So that's kind of the point. Here's the question, though. What's the acceleration? Scroll up. Let me see your answers to the previous problems. Okay. Yeah. What's your theoretical slope and how'd you get it? Okay. I see it. Okay.
Yeah,
So change in kinetic energy. And then you've got a calculation sheet. Can I see that 11?
Oh, I didn't upload it yet.
Okay.
But I have. I don't know.
What did you get for your equation right there?
Yeah, that was the other part I was a little confused on.
Okay.
Maybe hold it up to the camera and see if it'll work.
Yeah, let me take a look at that. Because your number looks good. So that probably means you did the right thing there.
Can you see? I can't really tell.
Just hold it still. Give me a second to read it. All right, I'm going to make that a little bigger on my computer here.
Yeah, so this is the question 9 and 10, and then 11 is all the way.
Yep. Okay.
That's the one I've circled is the equation.
Now you have velocity final squared, and then you drop the squared.
Yeah, but then I wasn't sure where I should end.
Okay. But the thing you put a box around, I think, is good. Y final minus Y initial is what you put on the x-axis. That's your displacement. It's either the mass is changing Y or the horizontal motion of the cart. And so it looks like your slope is 2 times M2 times G over the sum of M1 plus M2.
I think so.
Now, the only thing I don't understand necessarily, I worry about that negative sign. Yeah, okay, you can pull that. You can pull that away. So it seems to me you've got back over here. You've got velocity squared, and that's actually final velocity. If I remember what you had there, you had 2, and I'm going to ignore that negative sign. Figure out why that negative sign shouldn't be there, because it shouldn't. You had 2. I think it was M2G over M1 plus M2, that's a 1. I don't know why I crossed it. All right, give me my drawing tool back now. M1 plus M2. And then next to it, you had, I think it was Y2 minus Y1.
Yeah, like Y final minus Y initial.
Y final minus initial. Okay, so we'll go.
I did eventually just change that to the change in X instead.
That's delta X. It's either delta X or delta Y because they move together, right? One drops, the other moves at the, so that's the same. So in this case, if you put this on the Y axis, like you did, right? You put this on the Y axis and you put this on the X axis. Well, the thing that's out front that you multiply by, that's the slope, isn't it? So hopefully that's how you got this 1.78 number. You went 2 times whatever mass 2 was, and I forgot what the value was, times G divided by the sum of the two masses. One of them was 100 grams and 1 kilogram. So I think the denominator here is 1.1 kilograms. And the falling mass was 0.1 kilograms, if I remember right. And so that's what your slope is. That's what this theoretical number is right here. It's the things in the parentheses right there.
Okay.
I mean, does that make sense of what the point is? Yeah, we've got our conservation of energy equation, which allows us to see how velocity squared, this piece right here, relates to the displacement. It should be a straight line, go figure. And the slope of that straight line should be that thing in the middle, right there. Okay. And it looked pretty good. 1.78, 1.6. So what is that? That's like 1 part in 16 difference.
Yeah, I got 9.3.
Yeah, which is in a physics lab, anything under 10%, you're kind of happy with. You got reasonable agreement right there. Okay.
Okay. So what should I call it then if it's not like the physical quantity for
I think it's actually twice the acceleration, isn't it?
Okay, it's twice the acceleration.
It's twice the acceleration. I think if we actually had taken velocity versus time curve and taken the slope of it, I think we would have gotten about 0.8, about half of what you got right there.
Okay.
And the reason the only reason I'm deciding that is I'm looking at the basic kinematics equation, and I see that's what you got on the x-axis, that's what you got on the y-axis. That's twice the acceleration from that equation back in chapter 3.
Yeah,
but it has the same units of acceleration. That's the good news.
Yeah, so that's why I put acceleration, because it was meters per second squared.
Right, but it's actually twice if you remember that old kinematics equation from chapter 3.
Yeah, and I think we had to do that in other labs too. So yeah,
I think we did one time. Yeah, and to relate that. All right, does that answer your question?
Yeah.
Like you're ready to upload then today, because pretty good. This number right here, your 0.97. That's because of that little glitch, which is probably my hand being tracked by the motion sensor when I let the cart go.
Yeah. Okay. Yep. All right. Thanks so much.
You bet. Have a good day.
You too.